So this is basically a random lecture, and in this random lecture I'm going to talk about that how various types of crystal structures like polonium, iron, gold, diamond and sodium chloride are visualized using GDIS and XCrysden. So for this, first of all, let me talk about the polonium. So if I recall polonium is basically a simple cubic structure. It is simple cubic structure, and it means if I am having it understanding of what we call its lattice vectors and position of atom, then I can easily visualize it. So first of all, let me open a file means which I made here. So here, if I try to look at this file, so here it is a FDF file, free data format file, and you can visualize this using a tool known as GDIS. So that means to visualize this I will use a tool GDIS. It is available in Linux as well as Windows environment. It is available in both Linux and Windows environment. So I am using Linux environment, but you can also just a minute, Windows. Right, so I am using here Linux environment. So first of all, let me understand the structure of this. So so let me open. You can open this file in any editor also. So here basically this is the system level, means I am talking about the polonium. So let me write down it as Pu. Number of atoms in a unit cell, means simple cubic cell, number of atoms will be 1, and here only one type of species I am using, that's why it is 1. And first species is the polonium, so this is this, and it is the atomic number of polonium, and this is the lattice vector of this. These are the standard value, and I put single atom at the origin or in the center of the not but at the origin, means it is like this. If I try to understand this, means I am having a this type of situation. This is one cube, so that means if I place one atom here, then this unit cell is repeating itself in all the directions. It is repeating in this direction also, and in this direction. This is also repeating in this direction also, and this unit cell is also repeating in this direction. So that means when I place another cube over this, that means this atom will be placed here, and similarly when it is placed in this way, this atom will goes to here. I will show you in the later on. So that means I have taken only one atom in the unit cell. So this structure can be directly opened with the help of GDIS. So let me come out of it. Means if I in a terminal give command GDIS pu.fdf, then this file will be open in front of us. So this is a one polonium atom inside a box, and when I keep on repeating this, means it is like this, and like this. So that means a crystal, three-dimensional crystal of polonium will be generated, right? So this is a simple way to look at it. Even we can also make a FDF file using this also, or CIF file. So for that, let me open GDIS somewhere. If I open GDIS, and in GDIS, say if I take a one atom, go to here in the model editing, and say I am talking about a polonium, so I added a one atom polonium here. So sorry, first of all I go to the new model, then add atom. I placed any atom here, and let us call it as PO. I write down here PO in the level, and then enter. After that, let us place this atom in the 0, then enter, put it here by coordinate also 0, and then enter, again 0, and then enter. So that means one atom is placed here. Go to the normal board. So this is the position of polonium atom. Even we can also place this atom at the 1 1 1 also, one and same thing, because the unit cell is replicating itself in all the directions. So that's why either I will put it at 0 0 0 or 1 1 1 or 0 0.5 0 0.5, means in the center of the cube. So first of all, let me confine this inside a box. So for that, I go to the here set model editing, go to here transformations. So that means 1 1 1, but the lattice constant of polonium is basically the lattice constant of polonium is 3.34. So in place of this, let me write down 3.34, and 3.34. So these are the lattice vectors. So alter lattice periodicity is 3, and click on this, and this is confined. So this is a way, and I can save it also. From here I can save this as either in the po.cif file, or I can save it also as a po.fdf. We can save either in the Cartesian coordinates or in the fractional coordinates. If I tick it, then it will save it as a Cartesian coordinates, otherwise it will save it as a fractional coordinates, right? So that this is it. So if we go back to the folder where I have saved it, in the structures I have saved it as, say, this I have saved. So that means this is the structural information, and these are the few other flags for Siesta code, but need not to use me, because structural information is more important. That's what I have shown you here. Yeah, it is here. So this is more than enough to understand a structure. Similarly, after polonium, let me go to the iron. So if I try to understand it, means the structure of iron. So first of all, what should I do? To iron, what I will do, I open a terminal here. So fe.fdf. So let me understand it. So if I try to understand iron is basically BCC lattice, and these are the lattice vectors of FCC lattice. So let me show you that how these comes out to be, and this is the position of the atom inside the box. So this is in the primitive mode. This is in the primitive mode. Let me show you that how these things are coming out. So for this, let me open again it, So for that, what should I do? Let us make a, let us make first of all a unit cell. This is one. Right, then let me draw one more towards this side. One cell is this way, and another cell is towards this way. Let me, very interesting thing which we have to keep in mind. This is very interesting structure. Similarly, let me draw another this way. Right, so this is our main cell which I am talking about. Means the one atom is placed at here, at the center, and another atom is in the center of the cube. So that means this cell is replicating itself. So that means when I place this atom here, this unit cell here, so that means this will be here and another atom will be here. And similarly, if I put it here, so that means this atom is here and another atom will be here. So if I join the nearest neighbors, so that means if I join this atom with this, and this atom with this, and this atom with this, so that means these are the nearest neighbors which are joined. Another atom will be no, it should not be there. Let me choose the atom. It is this way. It should be little bit here. Let me join it. When I join this, it can be joined this way. So if I try to look at, because we need three vectors, so first of all let me call this as x-axis. Let me call it as let me call this as x-axis, let me call this as y-axis, and let me call this as z-axis. So if I join these, that means if I join this and this, means I draw a line parallel to it. This is one and this is another which I have drawn here, and So basically this cell which I have drawn, basically this is the primitive cell. So let me recall its vectors. So it is say this is the central atom, sorry, this is the central atom, and if I recall these three vectors, this is one vector, this is another vector, this is another vector. So this is the body center of this cube. So if it is the body center of this cube, that means its coordinates are 0.5, 0.5 and 0.5. Just a minute. Similarly, it is along negative z axis, so its coordinates are along 0.5, 0.5 minus 0.5. So these are the lattice vector of this, and this one is along negative x-axis, so its coordinates are minus 0.5, 0.5 and the 0.5. So that means the lattice vectors of BCC lattice are 0.5, 0.5, 0.5, then 0.5, 0.5 minus 0.5. Similarly, it is minus 0.5, 0.5 or 0.5. And sometimes it can be written like this, means this is also possibility 0.5, 0.5. You can follow any solid state physics book for this 0. Sorry, it is this one, and or you can take this as positive, and yeah, 0.5, 0.5, 0.5 minus 0.5. Any you can choose for the BCC lattice, right? So that means when I take one atom in the unit cell, that means I am taking a one atom in the primitive cell. One atom in the primitive cell. So let me visualize it with the help of GDIS. So this is the in the primitive mode. So if we try to look at this, means if I try to visualize it, it can be visualized in this way: GDIS Fe dot FDF. So this is the one atom which I have come to find. It looks similar as I have drawn. So if I repeat it, I am having the actual structure of iron in the primitive mode. But in place of this, if I draw this, means this one, here I have taken two atoms, because one atom is at the, it's a simple cubic like structure, but one atom is at the corner and another atom in the body centered, which I have shown here. Let me first of all try to look at its file, means FDF file. Yeah, see, sorry, first of all let me see it, and then I will show in the visualization software. Here in this case, these are the number of atoms I have taken, 2 inside the unit cell. This is the information about iron atom. This is the lattice constant. So these are the lattice vectors for the simple cubic. But if I recall another one at the same time, just a minute. Yeah, so if I try to look at, say, these are the lattice vectors for the BCC, means these are the lattice vectors corresponding to, that means I am talking about the primitive cell I am considering, right? But on the other hand, if I try to look at this part, means in this part, so in this case I have taken here for the simple cubic. But if I am taking simple cubic cell, then I have to take actual number of atoms. Means here I am taking 2 atoms. I am taking 2 atoms, one at the 0, 0, 0 and another atom is at the body center, and body center atom is recognized by 0.5, 0.5 and the 0.5. Also the atomic coordinates are the fractional. So let us visualize these two structures now with the help of GDIS one by one. So it is a GDIS FE dot FDF, and yeah, first of all let me look at this. Also open another one also from here. Let us see two one by one. This is the 1 atom per unit primitive cell, and if I keep on repeating it, I am getting whole of the iron. But on the other side, if I try to look at this, these are the 2 atoms in the simple cubic cell. This is the another way to look at this structure. This is also iron. So that means till now I talked about the simple cubic structure and the BCC structure in the primitive mode and in the simple cubic mode, right? Now I will talk about the gold structure also. So similarly, in the similar fashion, I have also 2 files for gold, means yeah, say AU1, AU underscore 1 and AU dot FDF. So let me first of all open AU dot FDF. So if I try to look at here AU dot FDF, so in this case I am also considering it as these are the face centered atoms, these are the lattice vectors corresponding to FCC lattice, and here I am considering primitive mode, means per atom per unit cell. But in actually FCC lattice must contain 4 atoms. So for that I have to take here this part as a simple cubic mode. So first of all, let us understand that how these lattice vectors are coming out for the FCC. So for FCC, if I recall, in case of FCC, sorry, some problem with it. Yeah, let me replot it this way. Yeah, so 1 atom is at the corner and other atoms are at the faces. So 1 atom is here, another atom is at this face, and third one atom is at this face. These are the FCC. So if I join these atoms, means if I join this with this, just yeah, let me join this. So let us join this. Means we for draw a unit cell we need 3 vectors. So once these vectors are there with us, we can complete the unit cell. So that means if I do this way and if I do this way, then this is the primitive cell inside it. So this primitive cell contains only 1 atom. Primitive cell contains only 1 atom. On the other hand, FCC lattice, actual FCC lattice contains 4 atoms. So let us understand it more clearly. So here this is basically the primitive mode. But if I try to look at the another file, see here what I have did, I have taken this is also in the simple cubic mode. These are the vectors corresponding to simple cubic mode, but here I have taken 4 atoms per unit cell. One atom is at the origin, and this one atom is at the one plane, xy plane. This is yz plane. This is in the xz plane. Means this atom in the center of xy plane, this atom in the center of yz plane, and this atom in the center of what we call xz plane. So let us understand these with the help of our visualization software. So GDIS, yeah, first of all let us understand au.ftf. So for au.ftf, this is in the primitive mode, and when I keep on repeating it, I will get the actual structure. It will also give me the similar structure as I can see from what we call au_1, where I have taken 4 atoms per unit cell. This way, this is also similar structure, but not in the primitive mode. Right? So there are 2 ways to look at the atoms. Now after this, let me talk about another very interesting structure, that is the diamond, and then after diamond I will talk about the sodium chloride structure. So diamond is basically what? Diamond is basically, if I go to the definition of diamond like structure, so that means it is also FCC like structure, but it was little bit different. Diamond is little bit different than but FCC. Means this is one FCC lattice, suppose this is the body diagonal of it. I join this part, sorry, let me join this end to this end, and if I join these 2 ends, that means this is basically the body diagonal. This is the body diagonal, and if along body diagonal up to the 1/4, say this is the 1/4 distance, this is the 1/4 distance, let me call it as the 1/4 distance. So from 1/4 distance, I will suppose this is 1/4 distance, and from 1/4 distance I will draw another another unit cell this way. Right, let me draw. Oh, sorry. Up to here. Just a minute. Let us assume this is the 1/4 of the body diagonal. So if it is 1/4 position, then I will draw another. Oh, sorry. This is a little bit tricky to plot it here. It means it is up to here, and this is 1, 2, 3, 4, and 5. Yeah, it's this way. It's better. Yeah. Then we'll finish it. This way, this way, and this way. It is this way, right? So that means just like this. So that means one atom is placed, means one atom is at this center, one atom will be here, another will be at this face, another atom will be at this face, and another atom will be this face. Similarly, when I look at the another one, means one atom will be lying here, another atom will be lying here, another atom will be lying here, and another atom will be lying here. So this is the basically diamond-like structure. So that means it contains 8 atoms. But here there are 2 FCC lattices, and they are merged along body diagonal up to 1/4. Up to 1/4. So in the primitive mode, one atom is at the 0, 0, 0, and another atom is the 0.25, 0.25, and the 0.25. This is the primitive mode. This is the one way to look at it. But these are the 8 atoms, and how these 8 atoms are arranged means one atom is at the 0, 0, 0, 0.5, 0.5, 0.5, 0.0, and then it is 0.5, 0.0, 0.5, then 0.0, 0.5, 0.5. Then means these are the atoms in the blue colored box, and in the red colored box the atoms are here, means every atom is displaced by 0.25. so it means when this atom is displaced by 0.25, so its coordinates are 0.25, 0.25, and its coordinates will become 0.75, 0.75, and 0.25, and this will become 0.75, 0.25, 0.75, and its coordinates will become 0.25, 0.75, 0.75. So these are the situation which we are getting. So let me put all these inside the FDF file and try to visualize it with the help of what we call GDIS, right? So here, GDIS, it is the diamond.ftf. so these are the 2 atoms, and they are behaving like what we call actual diamond like structure. See, it's like a diamond like structure. Similarly, and let me have a look at it. Diamond.ftf. See, these are the positions which I have already described here. See, this is the lattice constant, and these are the lattice vectors of the FCC lattice, and one atom is at the corner and another atom is at the 1/4 of the body diagonal, along the body diagonal, which I have placed here. In the similarly, when I go back to another atom, not another atom, but another structure where I have contained 8 atoms parent cell. Say, let me go back to, see here there are, see, these are the 1, 2, 3, 4 atoms in the first cell, first FCC cell, and these are in the second cell, second FCC cell. Means every atom is displaced 1/4 along the body diagonal. That's why this 0 will become 0.25, 0.25, 0.25, and here I have taken 8 atoms in the unit cell. So means this is translated along the body diagonal by 0.25, 0.25, 0.25. Similarly, this is this, sorry, let me change the color, that will be better. Yeah, after this, yeah, this will become this, and this will become this, and finally this will become this. See, every atom is displaced along body diagonal up to 1/4, right? So this is an another way to look at the diamond like structure. So let us have a look at this visually with the help of GDIS. So GDIS, it is a diamond _1. See, this is the structure which we have seen on our textbook so many times. So this is a diamond structure actually. So this is it. And after that, let me talk about the sodium chloride structure. Sodium chloride structure is also very interesting. So for that, here I have shown different sodium chloride like structures. For example, this is one sodium chloride structure, this is another, and this is the third one. This is a very interesting comparison. Let me open it with the help of another app if it is possible. Oh, it's not possible. No, it's not possible. Let me open it in the G editor. Now see, it's a very interesting structure. So here, this is also FCC like structure. One atom is at the, means if I look at it in the primitive mode, because here I am taking lattice vectors in the FCC. So one atom is lying at the corner and another atom is at the body center. So at the corner, which atom is lying? Chlorine atom is lying, because chlorine is indicated by 1 here, and similarly sodium is indicated by 2, so it was shown here, right? So chlorine as a corner atom, and body center atom is what? Body center atom is sodium, right? This is the primitive mode, but I am not talking about the primitive mode. Let me change the way. Yeah, this is another way to look at it. Means, but here I have taken this as a lattice vector in the simple cubic manner. So that means I am taking 8 atoms. So that means, what does it mean? This one atom is lying at the center, corner, and this atom is the face center. It is the face center atom. It is also face center atom. Means these two coordinates tells us about that. It is also face center. It is in the XY plane, and this one in the XZ plane, and this is in the YZ plane. But if I try to look at it, this atom is basically body center. This atom is basically body center, and this atom is the edge center, because this is 0, this is 0, so this is also edge center, this is also edge center. So these are the edge center atoms. So here these 4 atoms basically represents chlorine atom, because 1 is indicated by here chlorine and 2 indicates the sodium atom. So these 4 atoms corresponds to sodium atom. This is the one way to look at it. So I have also looked at this in a different manner. Rather than writing here 0 0 0 0 0 0 means let me change the color. Yeah, in place of 0 0, this 0, this 0, this 0, this 0, if I place 1.0, then that means I am taking one FCC lattice like this, because here this is the FCC lattice. So I translated another unit cell like this, as I did in case of diamond like structure, and I translated it along the body diagonal up to this position. So corresponding to this, because one atom is lying here, so corresponding to it another atom is lying, this is the face center, this is the backside face, so this atom goes to this position, and this atom goes to this position, and this atom goes to this position, and similarly this atom will goes to on this face lying, it goes to the another face. So that means in this way it is a little bit difficult to understand, but it is very simple. See, so these are the coordinates which I am talking about here, right? And if I try to look at either this structure or earlier structure, both looks identical. This structure where I put 0 0 0 here, and this structure, these both looks identical. So let me try to look at these structures with the help of our tools. So GDIS NaCl dot FDF, this is one structure, and another structure is also there with us, NaCl underscore 1 dot FDF. Let me open it, and similarly NaCl underscore 2 dot FDF. So these are the two structures, this one structure and this another structure, both looks identical, whether it is Cl1, and this is in the primitive mode. Here I have taken 8 atoms per unit cell, but it was little bit difficult to visualize these. So for that I have also I have also made a XSF file. So XSF file is also similar to it, but here I am putting coordinates in the actual format, and its lattice vector is basically, because it is the FCC lattice vectors, so say lattice constant is basically what, for NaCl the lattice constant is 5.63, and lattice vectors are 0.5, 0.5, 0.0, and similarly 0.5, 0.0, 0.5. So it is 0.0, 0.5, 0.5. So here what will happen, this 5.63 when put always here, so it will become, means 5.63 when multiplied by 0.5, it gives us 2.815. So these are the values which I have placed. So these are the lattice vectors corresponding to FCC which we have to put, but atoms are placed in this way. So this is the one atom and this is the another atom, so it is in the body center, so it is the half of this, right? So this is one way to look at XSF file, and similarly I have also plotted the FCC files for another XSF files also, because it was for NaCl it is very easy, yeah, or we can say that it is it can be visualized easily with the help of XCrysden rather than GDIS. So that's why I have shown you here about this one, XSF file. So this is the layout of XSF file, and this 17 corresponds to 11 and 17 corresponds to the atomic numbers. This 17 corresponds to atomic number of sodium, chlorine, and 11 corresponds to atomic number of sodium, right? So here these are not fractional coordinates, but these are the actual coordinates. Similarly, we can have a look at another file also. Say these are the three files. So let us look at, this is one file corresponding to primitive mode. This is one file corresponding to 0 0 positions for the sodium atom. This is 0, this is 0, but rather than 0 0, if I put 1 1, then things will not change, because periodicity take care so many things. Say this is the actual value. So what do I do? Let me try to open these files. So let us open XCrysden here and go to the file, go to the open structure, XSF file. So this is one file, NaCl XSF, right? So this is the NaCl structure. So here it shows, because these are contributed, because corner atom is contributed by every 1/8, so 8 corners are there, so overall its contribution will be 0. So but in the primitive mode, if I click it here, means 2 atoms per unit cell, and if I repeat it, number of units drawn, yeah, so this is the actual structure of the sodium chloride. See it. Similarly, we can open another structure. For example, let me close it and then open again another structure, another XSF file, means see NaCl_1.XSF. it also looks similar, right? So if atoms are not connected, then you can also change, modify, go to here, atomic radii. If I change atomic radii a little bit here, because default radii is sometimes smaller and bonds are not visible, so if I update it, say it is the sodium chloride structure. That's what we can see in various texts, and in the primitive mode it can be shown like this. And if I keep on repeating it, yeah, this way, this way, this way, yeah, you can see it. Similarly, one can go to the close it, and if I look at the another structure, XSF file, means NaCl XSF, NaCl_2XSF, this file. So if I open it, I will get similar type of structure. In the primitive mode, I can see it in this way. So when I repeat, it looks similar as I have seen earlier. For example, go to the modify atomic radii. Let me change it little bit. So if I repeat it, then it gives me the similar type of structure. It gives me the similar type of structure of sodium chloride. So this is it. So here in this lecture, I talked about that how various types of structures can be visualized in the primitive mode or the simple cubic mode. So if I take a simple cubic cell, then we have to take the large number of atoms in the unit cell. But if we have to take the smaller number of if we take this primitive mode, then we have to take the smaller number of atoms. So thanks for watching this video.